This is part 2 of chapter 19, Chemical Thermodynamics. So in part 1 we reviewed some stuff from Gen Chem 1, which was in chapter 5, and we also talked about, well, that included the first law of thermodynamics. We also talked through some vocab words: spontaneous, non-spontaneous, reversible, irreversible. Reviewed a little bit about enthalpy, delta H, entropy, delta S. And so part 2 is us taking a deeper look at entropy. So we're going to spend a lot of time looking at entropy here. So entropy is, again, it measures randomness or disorder. Either of those words work. I usually call it disorder. That's just the one that I kind of stuck to. So entropy is a state function, which means when we're measuring it, all I care about is the first number and the last number, the initial number and the final number. And so to calculate the change in entropy, final minus initial, works. But lab data, there's no like entropyometer or something. There's no instrument that you just stick it on something and it measures the entropy. So we have to have a way of collecting lab data and being able to convert that into an entropy. So that is what the second equation, the delta S equals Q ReV over T. So Q stands for heat, and the ReV just means for a reversible process. At the end of the day, it doesn't super matter. T stands for temperature, must be in Kelvin. The units on delta S are joules per Kelvin. So this is a very literal, this equation is very literal. The heat is going to come, we need the heat to come out in joules, there, and the temperature to come out in Kelvin, so I can take joules divided by Kelvin. So we're going to do a quick reminder of some stuff from chapter 5 on how to calculate heat, how to calculate Q, because we'll have to be able to do that before we can use that equation. So the first, well, actually all three of these equations came from chapter 5. So Q equals M times C times delta T is the equation that we use when we did calorimetry. So M stands for mass, typically in grams. C stands for specific heat, typically in joules per gram Kelvin or joules per gram degree Celsius. And delta T is, well, change in temperature. And the units can be either degrees Celsius or Kelvin. It does not matter which, because delta T means final minus initial. And if you subtract two temperatures that are both in degrees Celsius, or those same two temperatures, once they're both converted to Kelvin, you get the same thing, because the size of a degree Celsius and the size of a Kelvin are the same. So if something goes up by 10 degrees Celsius, the temperature also went up by 10 Kelvin. Since it says delta T, it doesn't matter the units as long as the final and the initial are in the same units. So we use that equation when we're heating something up or cooling something down, when it's changing, or it's not changing the state of matter. So like I take liquid water and I heat it up, or I take liquid water and I cool it down. Once I take liquid water and try to turn it into gaseous water, that equation doesn't work. So our second equation, Q equals N, which typically stands for moles, times delta H of vaporization or fusion or sublimation. So this is a constant that every chemical has that's typically in the units of kilojoules per mole that tells you how much energy it takes to vaporize, boil, undergo fusion, which is melt, or sublime, which is sublime. Just a reminder, sublime is solid to gas, melting is solid to liquid, and boiling is liquid to gas, just in terms of states of matter. So all we're really doing here, this equation, is just taking the value delta H kilojoules divided by moles times moles to get our answer in kilojoules. It's really just canceling out the unit moles. And then the last equation is using a table of standard enthalpy of formations and using the definition of, oh, I forgot, this is supposed to be a delta. Delta H of the reaction, or the change in enthalpy. Now, it's like, oh, those are solving for Q. Why is this one all of a sudden solving for H and it's on the same slide? Enthalpy is equal to heat at constant pressure. This is another one of the beautiful things coming from chapter 5. So if you can solve for heat or solve for enthalpy, sorry, delta H, that's equal to Q. So you can just take products minus reactants. We will practice that third equation, but we won't practice that until, I guess part 3, the next video, is when we'll get to practice that. Well, we're going to need it here in a little bit anyway, but no. Oh, I don't know what's happening. Okay. In Canvas, there is a file called Appendix C, Thermodynamic Quantities for Selected Substances. This is the table that lets us look up the numbers we need to take products minus reactants. So you're not memorizing this. This would always be given to you. We're going to refer back to it later. But, ooh, really little. Oh, and now he's got a thing. Alright, I should stop clicking. I'm gonna... Okay, degrees Celsius is special. We're gonna close that. We're gonna go back to the PowerPoint slide. Bam. Oh, I'm gonna put the... Nope. Stop being weird. Talking to myself. Okay. Nope. Yay! Okay, so I'm going to put a delta right there, because that should have had a delta there. And these are our 3 ways to solve for Q, which is the same thing as delta H. Okay, glorious. So what I want to do real fast, before we start our equation, we're going to practice using the delta S equation. So we did this at the end of the last video, or maybe it was in the middle, where we wrote just a quick reminder of enthalpy and entropy. So, the word enthalpy is the word that the symbol is delta H. And what this measures is the heat. Okay. Units are typically kilojoules or joules, although sometimes we see them in kilojoules per mole or joules per mole. Okay. When we have an enthalpy, the delta H value could be less than 0, which means negative, and that word is exothermic. That describes that. It means the heat is exiting, the heat is being released. Delta H could also be greater than 0, so the number could be positive, and that word is endothermic. And the ways we can solve for that, well, delta H of a reaction is going to be H products minus H reactants. I stole that from the previous slide. The summation signs in front of that just means the total of H products. We also, since Q is equal to H, I'm going to write Q equals M times C times delta T, and Q equals N times delta H vaporization or fusion or sublimation. Okay, so that's the ways we could calculate this. So now I want to look at entropy. So entropy is the word, delta S is the symbol, and it measures disorder. And its units are joules per Kelvin. That's it, joules per Kelvin. We have scenarios where delta S can be positive or negative. So delta S can be less than 0, which means negative. And that means there is less disorder, which can also be worded as more order. Things are more organized, they're less messy. Delta S could also be greater than 0, which means it's a positive number. And that would mean the disorder is increasing, so there'd be more disorder or less order. So the ways we can solve for delta S, well, the equation that we're getting ready to practice looks like this. We also have the one that was on the previous slide also said final minus initial. So I'm just going to reword that to products minus reactants, because the final are the products, and the initial are the reactants. So those are the equations we have so far to solve for delta S, and these are the equations we have so far to solve for delta H. Okay, so I keep writing this down. This table looks very similar to the one on the last video, except for I added the equations to this one, because there's really nothing on this slide that you don't have to know. Like, you have to know enthalpy is the word, delta H is the symbol. It measures heat, what its units are, what exothermic and endothermic mean. The equations, I'm not going to give you products minus reactants. That one you have to memorize, but any of the other ones I will provide for you. You need to know that entropy is the word, delta S is the symbol. It measures disorder, its units are joules per Kelvin. You need to know what it means if delta S is less than 0 or greater than 0. I will give you the equation that's Q over T, but you will have to memorize products minus reactants. And we're going to practice these a lot more, so it'll be fine. So the first law of thermodynamics was energy is conserved. Awesome. Well, this second video is all about entropy. It's all about delta S. So the second law of thermodynamics is all about entropy. It's all about delta S. So it's a two-part law. And it's not like I pick this part, I don't care about that one. It's an all or nothing thing. You gotta know part 1 and part 2 because together they make the second law of thermodynamics. So what this says is the entropy of the universe, the delta S of the universe, increases for a spontaneous process. Now, real quick, the last video we had some vocab, spontaneous and non-spontaneous, reversible and irreversible. Spontaneous is always equal to either reversible or irreversible. So try to think for a second if you can remember which one you think that is. And the correct answer is irreversible. So underneath spontaneous, I'm going to write irreversible right there. That word can be exchanged for spontaneous. So the entropy of the universe increases for spontaneous processes, or I could say the entropy of the universe increases for irreversible processes, and it's saying the same thing. Okay, so that's part 1. Every time we have a spontaneous or an irreversible process that happens, the disorder, the entropy of the universe gets bigger. Every time a spontaneous thing happens, the universe gets messier. The second part of the second law of thermodynamics is the entropy of the universe does not change for a reversible process. So when we have an irreversible process, the disorder of the universe gets bigger. We have a reversible process, the disorder of the universe doesn't change at all. Okay, so kind of like with the first law of thermodynamics, here's the words. Let's look at the equations. Like, what are the, what other ways could we say the same thing? So for a reversible process, delta S of the universe, the change of disorder of the universe, is equal to 0. So whatever disorder was increased or decreased by the system was lost by the surroundings, is what this is saying. For an irreversible process, irreversible processes are also spontaneous. Just reminding you of that. The words said the change in entropy of the universe increases. So delta S of the universe is greater than 0 whenever it's an irreversible or a spontaneous process. So that's in symbols, the second law of thermodynamics. The previous slide works. This slide works. I kind of like them both. The equations help me answer some questions, and the words help me answer other questions. So you're going to kind of have to play with it and see what you like the best. So we're going to jump into a math here. So we're going to read the question, and then we're going to give this a shot. So the normal boiling point of ethanol, which is right there, is 78.3 degrees Celsius, and its molar enthalpy. So enthalpy is, think about it, is it delta H or is it delta S? It's delta H of vaporization, okay, is 38.56 kilojoules per mole. What is the change in entropy, delta S, in the system when 68.3 grams of gaseous ethanol at 1 atmosphere condenses to liquid at the normal boiling point? So we're solving for delta S. So far we have two equations for delta S. Delta S equals Q over T, or delta S equals products minus reactants. We're going to practice the delta S equals products minus reactants later, And when you're given that information, you're going to be given a table, so you can look up what the products are and what the reactants are. You're also going to be given a balanced equation. When we are given lab data, that's when the delta S equals Q over T is useful. That's for lab data. Okay, this is lab data. So before we jump too far into this, the molar enthalpy of vaporization is 38.56 kilojoules per mole. So we need to stop and think, what is vaporization? Like literally, what states of matter are it? So when something vaporizes, it goes from liquid to gas. We okay? Okay, awesome. I'm going to read blah, 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 blah. We're supposed to solve for it when something condenses to a liquid. So condensing is gas to liquid. So if we look at our states, the number we were given was for how much energy it takes to go from liquid to gas. But we care about how much energy it takes to go from gas to liquid. So what we need to change is the sign. Because that's the difference between those, is the energy absorbed or released. When something condenses, it's going from a gas to a liquid, it's cooling down. So it's going to be a negative. It's going to be releasing energy. Okay, so I'm putting a negative right there based on the words. So we got to be careful with our words with this one. So delta S equals Q divided by T is going to be the equation that I use. T is not a problem. We were given the temperature at 78.3 degrees Celsius. What we got to do is convert that to Kelvin. And then we've got T. Q up here is the thing that we've got to work for. This needs to be in joules eventually, and this needs to be Kelvin eventually. We were not given joules or anything at all like joules. We were given a temperature, which we know it's going to go down here. We were given a delta H of vaporization. We were given a grams, and we were given a pressure. The pressure is only given because it's a gas at some point. So if we look back at the equations to solve for Q equals M times C times delta T. Not this, we don't have a change in temperature. Q equals N times delta H of vaporization or fusion or sublimation. That one, ding, 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 we've got a delta H of vaporization. So we're going to be using the Q equals N times delta H of vaporization equation. And that's going to be the numerator. That's going to go on the top here. Okay, so we have the delta H of vaporization. That's not a problem. The question did not give us moles. It gave us grams. So we're going to have to do some really tricky math using the molar mass of ethanol to convert to moles. So I took 68.3 grams of the ethanol and used the molar mass of ethanol to convert it to moles of ethanol. Okay, so I got moles. I have N. That's equal to N. So what I'm going to do is I'm going to plug this all together into the delta H equals Q over T equation. I'm just going to plug everything in there. So for Q, I plugged in N times delta H of vaporization, where I changed the sign. And for T, I took the 78.3 degrees Celsius and added 273.15 to it to get it into Kelvin. And if we look at the top, the numerator, the moles are going to cancel, leaving me in kilojoules, which is fine, but the unit needs to be joules divided by Kelvin. So I had to multiply it by 1,000, and that's where the negative 163 joules per Kelvin came from. So we were kind of utilizing two equations. We used the Q over T, but we had to use Q equals N times delta H to get the Q. Now, this is what I would expect. So we could do a calculation. Okay, wonderful. If this was a test question, I would have given you the molar mass of ethanol, so you wouldn't have had to look it up. But after I make you solve for pretty much every calculation, every number in Chapter 19, I'm going to ask a question after it. And the question's pretty much going to be, what does that number mean? So the delta S is negative 163 joules per Kelvin. I want to know, what does that number mean? Well, we have to think back to the chart that I made just a little bit before this about when delta S is positive or when delta S is negative. When delta S is less than 0, which means negative, that means there is less disorder or more order. So after you did your math and got negative 163 joules per Kelvin, I'm going to ask, what does that mean? And your answer would be either less disorder or more order, or both of them. So you're going to have to be able to take your number and tell me what it means. And that chart that I've been writing down, that's how you're going to figure that out. Now that chart's going to be in your brain. But for right now, we can refer back to it. Okay. So here's another question about entropy. This one is a little bit different. It's more of it's not so much a calculation, a little bit of math, but not really. So based on the second law of thermodynamics, so that was that two-part law, if a process is spontaneous, which also means it's irreversible, and the system has a change in entropy of 11.5 joules per Kelvin. So change in entropy means delta S. I'm just writing down the symbols because words, I'm trying to make them symbols. What is true about the surroundings? Okay, before we look at numbers, when you think back to the second law of thermodynamics, there were two parts to it. One about when it's spontaneous and one about when it's reversible. At this point, I'm being told it's spontaneous. So I don't care about the reversible part at this moment. The second law of thermodynamics, what it says is delta S of the universe is going to be greater than 0. It's going to increase. The change in disorder of the universe is going to increase every time something spontaneous happens. Okay. So delta S of the universe is just delta S of the system plus delta S of the surroundings. And we know that when I add those two together, I'm going to get some number greater than 0. That's according to the second law of thermodynamics. So in this question, what they're telling me is that the system has a delta S of 11.5 joules per Kelvin. So this is 11.5 joules per Kelvin, which is true about the surroundings. So I'm trying to figure out what's true about that one. So I'm going to be super lazy about this, and I'm just going to go one by one and see what happens. So the first one says delta S is less than negative 11.5. So that's abstract. I need to have, like, in my brain, I have to have something. So I'm going to say, well, what's less than negative 11.5? I'm going to call it negative 12. So if delta S of the surroundings was negative 12, well, 11.5 joules per Kelvin plus negative 12 joules per Kelvin is not greater than 0. That would actually be a negative number. So what I'm trying to do is, what fits this? What will make this true? If delta S of the surroundings is negative 12, not okay. So I'm going to cross out A. I'm going to erase that now. Okay, so let's look at scenario 2. Scenario 2 says delta S is going to be greater than negative 11.5. And again, that's too abstract for me. So I'm going to pick a number that is greater than negative 11.5. I'm just going to go with negative 11. So if I took 11.5 joules per Kelvin plus negative 11, hey, that would get me 0.5, which that number is greater than 0. So that is working out. Okay. I want to go ahead and check part C. So part C says when delta S is equal to negative 11.5. So if this was negative 11.5, well, if I took positive 11.5 plus negative 11.5, wouldn't that be equal to 0? So not greater than 0. So that one doesn't work either. So my answer is B. Can you think of a scenario in which if I had changed the question, part C would have been true? Thinking about the second law of thermodynamics. So the second law of thermodynamics has the spontaneous section and it has the reversible section. The reversible section is when delta S of the universe is equal to 0. So part C would have been true if it was a reversible reaction. So that wasn't the question, so that's why C is wrong. But just how I could have changed the question and gotten a different answer. Okay. So we're still talking about entropy. We've practiced some of the math, but now we're going to talk about the molecular interpretation of entropy, which means think of it on the molecular scale, like as atoms and molecules. You guys are so lucky that this is a video, because usually I dance for this and I'm not recording that. That's not happening. So, I don't know how I'm going to do this, because I'm going to totally move my arms. We're just going to keep going. Okay. So, when we're talking about entropy, we're thinking about it, like I said, from the molecular perspective. If we think about how temperature is going to affect entropy, so again, entropy is disorder. When you take a sample of something and you increase the temperature, what that does is it increases the kinetic energy, the energy of motion of those molecules. So they're going to move faster and have a chance to probably move further away from each other. So when you increase the temperature, that's going to make the molecules move faster, which should make them have more disorder. Okay, so we're going to come back and look at that. But just in general, the higher the temperature, the more disorder there is. Okay, so talking about, we increase their kinetic energy. These are the different ways that a molecule can use its kinetic energy, like the ways a molecule can move. So this picture down there is water. That's going to be the example. So the first is translational motion. So when a molecule gets more energy, it can have translational motion, which means it moves left or right or forwards or backwards or ups or down. It literally moves. It changes its location. It walks over to a new spot. Translational motion is like if it were a molecule, it would use its feet to move somewhere else. Okay, so translational motion, left, right, forward, backward, up, down. Vibrational motion is another way the molecule can move. In a vibrational motion, the molecule, if it's only doing vibrational motion, it's not moving left, right, forward, backwards, up, down. It's staying in the same location, but its bonds are moving. So that's what the picture down here, this part, is. Okay? So this first one is trying to show the molecule where its bonds are stretching. So if you think of make a fist in your left hand and make a fist in your right hand, and think of the rest of your body as the oxygen, as the red atom, and your left fist and your right fist are the white hydrogens of the molecule. What's happening is the bonds are stretching out. So it's like if you stretch your arms away from your body, like you're stretching in the morning when you wake up. That's what's happening, is the bonds are actually extending and moving away from the oxygen. The second one, this guy, okay, is if you put your arms out to the side, so you're kind of like flat, like your arms are directly to the left and right of your body, and then move your arms in towards your body, so you're smushing them towards your body. That's another way it can move. Or the third one is if, put your arms out again with your hydrogens. One arm stretches out and one arm pulls towards your body. So it's called an asymmetrical stretch because one side is going away and one side is coming in. I always feel like a cheerleader a little bit when I do this. You can't see me right now. I'm doing it anyway. Yikes. Okay. So that's vibrational motion. Oh, I'm going to have to erase this. There. And then our third type of motion is rotational motion. And you'll never guess this. It's when they rotate. So it rotates along the x-axis or the y-axis or the z-axis. It spins. Okay. So these are the three types of motion that a molecule undergoes. We have to talk about this because there are going to be times where we have to think about two molecules and compare them, and we have to go all the way down to this tiny scale of which one is going to do more vibrational motion or which one's going to do more rotational motion. So we have to actually know this. Plus I think it's kind of cool. Just this is what molecules do. Okay, so we're going to connect that. That's awesome and fun and whatever, but how does that compare to like big scale real life stuff? So Boltzmann is a scientist who was trying to take the micro scale, the vibrations and the rotations and translations, and connect that to the lab data that we get, like the numbers for delta S. So he called, if we could think of, let's pretend like we just have two molecules in our sample. That's never going to happen in real life, but we're going to pretend like we have two molecules in our sample. And they are at some temperature, at some volume, and they're doing their thing. Well, so they're vibrating, they're rotating, they're translating, they're moving around. So if I took a picture of those two molecules, yep, because that's the noise it makes, and then they moved, because they're still moving, and then I took another picture, and then they moved, and I took another picture, and I kept doing that until I found every arrangement those two molecules could have, and then when it started to repeat again, like they're back to the same arrangement that they had before, I would stop. Okay. Each one of those pictures is called a microstate. It is one arrangement of the molecules in a sample. Okay, so I think of microstates as pictures, like just, so anyway, okay, so microstates, that's what that's talking about. So microstates have the symbol capital letter W. So capital letter W stands for microstates. So trying to connect these microstates in the micro scale, the tiny scale, to the big delta S, or S anyway that we could calculate, Boltzmann came up with this equation, where S stands for entropy, K is the Boltzmann constant, which is given right there, ln is natural log, and W is microstates. We're not going to really be using this equation to calculate, because you're never going to be given a sample and say, hey, count how many microstates there are, take a bunch of pictures. Yeah, we can't see those molecules, so that's not going to happen. If anything, we would use the lab data to solve for S, and then, or to get our lab data to to get S, and then we would use this equation to solve for W. But I don't have a lot of times in my life where I'm like, I wonder how many microstates would happen if I have... No. What I want us to think about is what is the relationship between microstates. Like if you have a lot of microstates, what does that mean about your entropy? Or if you have very few microstates, what does that mean about your entropy? So if we think about W, if the number, whatever number is in W, gets bigger, think about this equation. If W gets bigger, won't that make delta S bigger? So more microstates gives us more disorder, because the more ways those molecules can, the more pictures I can take of my molecules trying to arrange themselves, the messier that it is. If there's only 3 ways those molecules can arrange themselves, it's very orderly. But if there's 47 million ways those molecules can arrange themselves, it's really messy. So the other version of the Boltzmann equation just looks at delta S instead of S. I'm not even going to tell you that I'm going to give you this equation, because I can promise you you're not going to calculate using this equation. What I want you to know about entropy and microstates is the thing that I wrote in green over here. The more microstates, the more disorder. So inversely, if something has very few microstates, there's less disorder. That's the arrangement that I want us to know out of this. Okay. So entropy increases with the number of microstates. That is what I want out of this whole thing. Okay. So what we're going to do now is we're going to look at the other scenarios. What else? What's changing other things? How does that impact the microstates, which will then impact the entropy? So we talked about this before, but if we have a sample at 5 Kelvin and I look at its disorder, and I take that same sample and I increase it up to 800 Kelvin, so I increased the temperature, what do we think is going to happen to the number of microstates and the disorder? Well, if you increase the temperature, they're going to move faster, they're going to move more, so there's going to be more different pictures that I could take, more different microstates. So if I increase the temperature, I'm going to see an increase in microstates, which will increase the delta S. So inversely, if I decrease the temperature, I make it colder, the molecules are going to move slower, so they're not going to have as many arrangements, so we'll have fewer microstates, which means lower delta S, so less disorder. So volume. Volume really only matters when we're talking about a gas, because if it's a liquid or a solid, it doesn't matter how big the container is. But if you've got a gas, you make the container bigger. Think about how that would impact microstates. So if I increase the volume. Well, if I increase the volume, aren't there going to be more locations for those molecules to be? So there's more different arrangements. So if I increase the volume, I'm going to have increase in microstates, which I know means an increase in delta S. So if I decrease the volume, there's fewer spots for the molecules to go. So there's fewer microstates and less disorder. The number of independently moving molecules. So if I had 3 molecules in my sample versus 19 molecules in my sample. So if I have, I'm going to use N to stand for this, just thinking of it like moles. If I have an increase in the number of molecules, isn't that going to mean I'm going to have more different pictures to take because there's more different things to arrange? I'm going to have more microstates, an increase of delta S. If I had fewer molecules or fewer moles, I'll have fewer microstates, and I'll have a lower delta S. Hopefully, we're feeling okay with that. Let me know. If not, we can go through this some more, but for now, yeah. The last thing before we're going to put this all together and actually answer, or ask, I'm going to ask, and I guess I'm going to answer too, questions about this, is thinking about states of matter. So comparing the entropy for solids versus liquids versus gases. So this is just a reminder of what molecules look like in the different states of matter. So just looking at it, remember entropy is disorder. Which one looks the most disordered? You might argue that it would be the water, because they're definitely not arranged. But if you think about the gas, their volume is going to be a lot bigger. So it's going to increase the volume, which will increase the number of microstates. So this is how the disorder of states of matter compare. The disorder of a gas is way bigger. It's more messy. Okay. Disorder of liquids and aqueous, we're going to pretty much put them together. It's squiggly line equals to, not exactly equals to, because there's all kinds of scenarios and we're not going to go there. But gases are more disordered than liquids and aqueous things. Okay. And solids have the least amount of disorder because the molecules can't really move. They don't have any translational motion. They only have a tiny bit of vibrational motion and maybe a little bit of rotational motion. So yeah, we're going to be using that. So this is how we're going to use all this information to answer questions. You've already kind of said all those things. So here's the questions. All right. There are 4 different questions here. I'm asking the same thing, but we're going to apply it 4 times. Will the following processes produce an increase or decrease in entropy of the system? So we're trying to figure out, will delta S be a positive or a negative number? Obviously, we can't actually calculate that. So we're going to have to stop and look at this situation and think about what's happening. So in scenario 1, carbon dioxide solid becomes carbon dioxide gas. So we need to tell by looking at this, is it going to get more disordered or less disordered? When I do these, I always start with states of matter. That's the first thing I look at in every set of these questions. So if I start with a solid and I end with a gas, just thinking about that, what do you think will happen? Will we become more disordered or less disordered? Well, according to the slide just a second ago, I said gases are more disordered than solids. So this will be a positive delta S. It's going to get more disordered when the carbon dioxide solid goes to carbon dioxide gas. Be a positive, an increase. Okay. Scenario 2. CaO solid plus CO2 gas, arrow CaCO3, calcium carbonate solid. Okay, so let's look at states of matter first. At the beginning, I have 1 solid, and I have 1 gas, and at the end, I just have 1 solid. So, if we're thinking about from the sides of the arrow, the beginning, the solid and the gas are going to be more disordered than the end. A couple of reasons. One of them is that there's a gas at the beginning and there's no gas at the end. But the other scenario, aren't there 2 moles of chemicals? There's 1 calcium oxide and 1 carbon dioxide at the beginning. And at the end, there's only 1 mole of calcium carbonate. So both of those things are telling me that it's going to be less disordered because we have fewer moles and we went solid and gas to just solid. And this one was because of solid to gas. Okay, so this one would be a negative and this one would be a positive. So let's look at 3. All right, gas plus gas, arrow solid, plus 2 moles of gas on one side, 1 mole of solid on the other. I'm going to go with a negative delta S. This is becoming less disordered. It's becoming more ordered because there's fewer moles and because gas became solid. Scenario 4. 2 CO, so gas, gas, gas. All right. Okay. So I can't compare states of matter for this one. I can't compare temperature and I can't compare volume because we weren't given that information. So let's compare moles. So at the beginning I have 2 SO2s and 1 O2, so a total of 3 moles. And at the end I have 2 SO3s. So fewer moles, negative delta S, a decrease in the number of moles. Hey, good job us. Let's do another type of question. Okay, so what we're going to do here is I'm going to... That's it. Nope, come back. Okay, so here's our scenarios. We have to circle, so there's 4 questions again. Question 1, question 2, question 3, question 4. In each pair, so like in question 1, we're going to read the starting scenario and the ending scenario, and we're going to circle which one has the most disorder, the greater entropy. So in question 1, if I have 1 mole of hydrogen gas at STP, so a quick reminder, STP stands for standard temperature and pressure, and that means 0 degrees Celsius and 1 atmosphere. So 1 mole of hydrogen gas at STP, or 1 mole of hydrogen gas at 100 degrees Celsius and 0.5 atmospheres. So just like the first question, I always look at states of matter first. So hydrogen gas to hydrogen gas. I can't answer the question based on that. Next, I look at moles. So 1 mole of hydrogen to 1 mole of hydrogen. Okay, that doesn't help me. So now I'm down to temperature and volume. Okay, so at STP, it's 0 degrees Celsius. So the beginning one is 0 degrees Celsius. The end one is 100 degrees Celsius. So based on temperature, the higher the temperature, the higher the disorder. So that one's leaning towards the 100 degrees Celsius. That's what that looks like. But I want to look at the pressure as well. So the first one starts at 1 atmosphere, and the second one goes to 0.5 atmospheres. Pressure never makes sense to me. I have to think about it in volume. So the relationship between pressure and volume. The higher the pressure, the smaller the volume. So 1 atmosphere is a higher pressure than 0.5 atmospheres. So the beginning scenario is going to be in a smaller container, and the end scenario is going to be in a bigger container. Bigger volume, bigger disorder. So all of the signs point to 1 mole of hydrogen gas at 100 degrees Celsius and 0.5 atmospheres having more disorder, having more entropy. So let's look at scenario 2. 1 mole of H2O solid at 0 degrees Celsius or 1 mole of H2O liquid at 25 degrees Celsius. So let's look at states of matter first. Start with a solid, then it goes to a liquid. So which of those two do you think has the most disorder? Liquid. Next I look at moles. 1 mole and 1 mole. That doesn't help. Next I look at temperature and pressure. We weren't given a pressure, but temperature. 0 degrees Celsius. This is 25 degrees Celsius, so bigger temperature. So that one would be my winner out of those two. Okay, number 3. 1 mole of H2 gas at STP, 1 mole of SO2 gas at STP. So states of matter. Gas, gas. Not helpful. Number of moles. 1, 1. Not helpful. Temperature, volume. They're both STP, so they're both 0 degrees Celsius and 1 atmosphere. Not helpful. Well, crap, I'm out of things. This is when we went through all of those scenarios, we still can't answer the question. We have to think all the way back to that whole vibrational rotational thing. If I just look at the molecules themselves. So H2 gas is not 2 hydrogen atoms. So they have 1 bond between them. SO2, that's 3 atoms, a sulfur and 2 oxygens. There's 2 bonds there. So if we think about it in terms of vibrations and rotations, the SO2 is going to have 2 bonds that it can wiggle and move around, where hydrogen just has 1 bond where it can wiggle and move around. So SO2 is going to be more disordered because of the bonds. And that's super nitpicky. But that can happen, and that's real life on things people have to decide between. Okay. So scenario 4. 1 mole of N2O4 gas at STP or 2 moles of NO2 gas at STP. So states of matter. Gas, gas. Nah. Moles. 1 mole to 2 moles. Hey, 2 moles is bigger. Temperature, pressure, they're the same. So I'm going to go with that. Okay. These are the types of questions you're going to have to answer. On Mastering Chemistry, it's going to be like drag them into the box. So hopefully we're feeling okay on that. You'll get to practice some in the Chapter 19 discussion worksheet. So definitely give that a shot and see how things go. So third law of thermodynamics is, I think, about the end, because this video is super long and I'm super sorry. Third law and then a couple of, okay, almost done. So first law of thermodynamics, energy is conserved. Second law of thermodynamics, that whole reversible spontaneous thing. Third law of thermodynamics, it's just a statement. The entropy of a pure crystalline substance, so the entropy of a solid at absolute 0, which is 0 Kelvin, is 0. So what this is saying, at 0 Kelvin, S equals 0. There is no disorder. There is only 1 microstate. So at 0 Kelvin, what this is saying is everything stops. There's no vibrations, rotations, translations. There's no movement at all. At 0 Kelvin, everything stops. Now this is still officially theoretical, because in the lab, they've not been able to get anything to 0 Kelvin. 0 Kelvin is, there is no heat at all. They've gotten well below 1 Kelvin, but not all the way to 0. I'm just going to trust them on this, my friends. But so the third law of thermodynamics, at 0 Kelvin, there's no disorder. There's only 1 microstate. So it's really, like I said, it's like a statement. Okay? It's still about entropy, though, so that's why it's included in this part. Okay, so this is just a graph kind of showing, if graphs make more sense to you, the things we were talking about, how entropy changes. So you can see that as the temperature increases, as the x-axis increases, the entropy, which is the y-axis, is going up. You see the third law of thermodynamics, because down here, 0 Kelvin, 0 entropy. That's the third law of thermodynamics right there. But the other thing that's interesting is you can see when something goes between solid and liquid, see how it jumps up? There's a dramatic increase in disorder. When something goes from liquid to gas, it jumps up as well. There's a dramatic increase in disorder. You can see that the change for liquid to gas is more, is a lot bigger than it is for solid to liquid. That's just because the differences between liquid and gas are a lot more different than solids to liquids. Okay, so this is where I want you to, if you haven't already, go to the chapter 19 Canvas page, find appendix C, and we're going to be using that. We're going to practice doing the products minus reactants example. So on this chart, this is a small version, a tiny version of the set of tables that exist for every chemical. We can, for every chemical, know from the table what its delta H, delta G, and its S value is. So if you look at the units here, I told you that S's are always joules per Kelvin. This says joules per mole Kelvin. All that's telling us is that each of these numbers represents the amount in 1 mole of that chemical. So if you have 2 moles, you're going to have to take the number from the table and multiply it by 2. Okay, so we're going to calculate, this is how we're going to do delta S. You're going to see a degree sign that just stands for standard conditions. It just means at a certain temperature and a certain pressure, and really it means it comes from the table. So it's the sum of products minus the sum of reactants. So we're just going to practice this. So words, how you're going to recognize these problems. I'm probably going to give you a table, and I'm going to have to give you a balanced chemical equation, like this maybe. Okay, so I just relisted the equation right there. I didn't write the N and the M before. That's just a reminder to multiply by the coefficients. So here's our balanced equation. Just a real quick reminder, these are the products, and these are the reactants. So when I do this, I'm going to add up all the products, and then I'm going to add up all the reactants and take products minus reactants. And I'm going to refer back to that table to get the numbers. So first I'm just going to set it up. So products, I'm going to take aluminum solid, this, I have to multiply it by 2. That's what the 2 is doing right there. Then I'm going to take H2O gas, and I have to multiply it by 3. Now you need to be careful, because when you look them up in the table, there's going to be an H2O liquid, there's an H2O gas, and there's an H2O solid. We need H2O gas. Okay, so these are the products. Minus, then I took all the reactants. Al2O3, there's only one of them, so I didn't write times 1. And then there's 3 hydrogen gases, so there's the 3 for that. So then I'm going to grab my table and find the number for this, and this, oops, and this, and this, and then just throw them in there. So for right now, you're just going to have to believe me that these numbers came from the table. If you have that table in front of you, look them up, you can see. The table for the units shows joules per mole dash Kelvin, and that's kind of gross. It's joules per mole times Kelvin is the actual unit, but I used the unit that's on the table because that's what we see. So now it's time to grab my calculator. Just make sure that you actually use parentheses. So it is going to be all of the products minus all of the reactants. So just be careful when you if you put all this in your calculator at once, make sure you put a parentheses around this and this, or else your calculator is not going to do the math that you want it to. I got a number at the end, 180.39 joules per Kelvin. The unit moles is gone because it canceled out when I multiplied it by 3 or by 1 or by 3 or by 2. Those were moles. Okay, so got a math, did a number. Good job for me. I'm going to ask at the end of that, what does that number tell you? That number is greater than 0, right? It's positive. So we have to remember what delta S greater than 0 means. That means there is more disorder or less order. And we know that because that number is greater than 0. The bigger it is, the how much more greater than 0 it is, the more disordered. So there is, it is a scale. Like the further away from 0 it is, the more it is either disordered or ordered, depending on which direction it's going.